I will start in like 5 minutes. I'll start in a few minutes. Okay, I'll share my slides. Right, so this is the third week of this live session. And again, like the previous live sessions, I'll spend most of the time going through a summary of what Sir discussed in his week 3 videos. And at the end, we'll go through some practice problems. So in the previous week, we were learning about solvent suppression, where basically if you have a sample dissolved in a solvent, say the solvent is water, The 1H protons of water will give such a strong signal that the signal of the sample will get suppressed. So here is an example of a spectra where water suppression has not been done. So you cannot at all understand the spectra of the sample here. It has completely merged with the baseline and appears as noise. So the thing to do is somehow this peak of water has to be suppressed. In the previous class, we had discussed a couple of methods of the solvent suppression. This is another method called the jump return sequence. So here what is done is first a 90-degree pulse is applied. So as you know, the net magnetization lies along the Z direction. And when you apply this 90x pulse, the magnetization goes samples and sample 1 and sample 2, and somewhere in between the sample you have the peak of water. So here they have been shown with different colors. The two samples are with blue and green and water is with red. So here the three arrows that you can see corresponds to the magnetization of sample 1, 2 and water. And after this 90-degree pulse, all three of these magnetization come from the Z axis to the Y axis. Now a time tau is given. During this time tau, the magnetization will precess in the transverse plane. But the special thing about this method is that the carrier is on water. What does this mean? This means that the observer is staying on the water magnetization. So imagine you are the observer and you're standing on the magnetization of water. So to you, it will apply that it will appear that the magnetization of water does not move at all. So the magnetization of water will simply remain along the y-axis, but sample 1 and sample 2 will precess according to their frequencies. Like sample 1, as you can see in this NMR, it lies more downfield, so it will have higher frequency, and sample 2 will have lower frequency. And because your observer is standing on the frequency of water, the observer will see that the water signal is stationary. It just remains along the y-axis. So after giving a time of tau, during which sample 1 and sample 2 move precess along the xy plane, after that time tau, another pulse of 90 minus x is applied. This is exactly the opposite pulse of what was applied previously. So because water has not moved, water will simply jump back from the y-axis back to the z-axis. As you can see, this red arrow showing the magnetization of water, it has just completely jumped back to the z-axis. This is because, as I said, the observer is standing on water. So according to the observer, the water signal is stationary. And if it is stationary, once it comes to the y, it will remain in y-axis. And if you apply a 90 minus x pulse, it will simply go back from the y to the z-axis. But what about the other two signals of sample 1 and sample 2? These two signals were precessing along the transverse plane. So when you apply the 90 minus x pulse, some component of these signals will definitely go back to the z-axis. But the other components will still remain as you can see here. So both the signals of sample 1 and sample 2 have reduced because some component of that signal has gone back to the z-axis. But because they were precessing along the transverse plane, some of the component will survive. After this, if you so after this 90 minus x pulse, the FID is collected and the Fourier transform is done. So if the FID is collected over here, as you know, we have already studied before, we put the detector in the transverse plane. In this particular case, we put the detector along this x-axis. So if the detector is along x-axis and the signal of water is completely along z-axis, detector will not pick up the signal of water. So you can see here the signal of water has been completely quenched. But the detector will see the signals of sample 1 and sample 2, and they will appear in opposite phase, because as you can see, one is along the plus x-axis and one is along the minus x-axis. So sample 1 and sample 2 will be observed, and the signals will come in opposite phase. And because the entire magnetization of water is along the z-axis, the detector will not pick up any signal for the water. So what this has done is that the signal for water, which was completely suppressing the signal of the sample, has been quenched. So now you can focus on the signal of the sample. The problem for this method is that suppose you have some signal which is close to the water, then that signal will also disappear. So that is one problem of this method. So normally, how do you know what the tau, like how much tau should be set? So suppose you set tau for very long, then the signal of sample 1 and sample 2 will also rotate and come back to the y-axis. And then if you apply 90x, they will also get quenched. So you don't want to do that. There are certain tau at which the signals will be maximum intensity. So normally that is screened by the machine, and the computer automatically screens that to give you what is the best intensity of the signals. So this is one method called the jump return sequence. So here again, it has been I'm continuing with the jump return sequence. So this portion shown here is basically this portion. So after the 90x pulse, you're giving time tau for sample 1 and sample 2 magnetizations to precess in the transverse plane. So what is the ideal tau that should be given? So if you know the angular frequency is omega, so 2 pi omega t is the angle traveled. So if we consider this angle as theta, this theta is 2 pi omega t, where omega is the angular frequency. Now, if this angle is 90, then the signal will be maximum because your detector is along this x-axis. So the condition, like I was asking in this slide, that what is the tau that should be set to have the maximum intensity signal? This is how you find that tau. You use this equation, 2 pi omega 1 tau, that is the angle traveled by the magnetization, is pi by 2. Because if it is pi by 2, it will be along the x-axis where your detector is. And so you rearrange this and you get tau is 1 by 4 omega. If you set the tau at this time, it will maximize your desired signal. So this method is often used in protein or DNA NMR, where suppose you have a protein NMR. A protein will have many amide protons around 7.5 to 10, and there will be aliphatic signals around 1 to 3. The signal of water here comes around 4.8. So basically here you can apply similar kind, and basically protein NMR is generally done in water because water is the most biologically relevant solvent that you have. So even same thing for DNA. In DNA, instead of the amide, there will be iminoprotons around 11 to 15 ppm. And basically both in protein and DNA NMR, since these are done in water, the signal of which comes around 4.8 ppm, this signal has to be suppressed. Otherwise, all these extra signals will simply come like noise at the baseline. So in both these cases, this kind of jump return sequence is done for water suppression, and you will get something like this where you have, so if you imagine here, the sample 1 and sample 2 are basically amide and aliphatic protons. So you can see sample 1, the one with the higher frequency, is coming at a positive signal, and the lower frequency sample 2 is coming at a negative signal. So here also in protein and DNA, the amide or immunoprotons will have positive signals and your aliphatic signals will have negative signals. And if you can properly adjust tau, then the intensity of these signals will be maximum and the water signal will be completely cancelled out. So this is the method for solvent suppression. Now we'll talk about a new phenomenon called spin echo. So what happens in spin echo? So again here, first a 90x pulse is applied. We'll imagine the simplest system, which is a one spin system. So the magnetization of the spin in the equilibrium condition is lying along the z-axis. When you apply a 90x pulse, it will force the magnetization to come along the y-axis. So this is your point 2, which is just after applying the 90x pulse that your magnetization is coming along the y-axis. After that, a time tau is given. During this time tau, this magnetization will precess along the transverse xy plane by a certain angle which we are calling theta. And this angle theta can be written as omega tau. So this is in radians. If we want it in degrees, it will be 2 pi omega tau, which we have already seen. So during this time tau that is given, the magnetization of the spin will precess by this angle theta, which we call the phase. Then a 180y pulse is applied. So how will you consider the 180y pulse? So this is the magnetization. It will have x. So after time tau, when it has a phase of theta, it will have x and y components. Now 180y basically means that you are flipping along the y-axis. If that is the case, then the y component will remain. So this is your x component, and this is your x component is here, y component is here. 180y, what this will do is it will flip the x component by 180 degree, but y component will remain same. So the net vector will be somewhere here, as you can see shown here, and this will also have an angle of theta, but in the opposite direction. So the 180y pulse, this is what it does. It will leave the y component unaffected and it will flip the x component by 180 degree. So after the 180 pulse, this is where your net magnetization will lie. Then you give a time of tau, and remember that the direction of precession will not change. So here also the direction of precession was clockwise. Now you have flipped the magnetization here, but the direction is still clockwise. So if you give it a time of tau, it will travel through the angle theta and it will come back along the y-axis. This is called refocusing. Why refocusing? Because suppose you have the detector here. When you are applying your first 90x pulse, your signal to the detector is maximum, which is this point, signal is maximum. Then slowly it is dying down as it is precessing. But after the 180y, you are flipping the signal and allowing it to again come back to, so these two positions are same. So you can see after the 180y, this is the 180y. After the 180y, you give it a time of tau and again the signal will reach maximum because it is again coming back to the same orientation. So that is why you're calling it an echo, because the signal is a maximum. So at point 2, directly after the 90-degree pulse, signal is maximum. Then after allowing it to precess and flipping it 180 degrees and giving it another time tau, the signal comes back to the same position. So this orientation and this orientation are same. That is why you are saying that the signal is refocusing, and you can see that it was these two positions correspond to this and this position where your signal is maximum because your detector is along the y-axis. So you are calling this a spin echo phenomenon. This process is frequency independent because no matter what the frequency of your spin is, it will refocus it back to the y-axis. So that is an advantage of this method. Now, suppose uh, the advantage of this method is that so we had seen in the previous class that there can be inhomogeneity in the field which will cause a phase error. So in this case, so here we have considered only one spin, but suppose because of the phase error, there were multiple spins. Each of these spins will get focused back to the same point after the spin echo phenomenon. So this is the advantage, that even though there are inhomogeneity in the field, all the inhomogeneities will get refocused and you will get a strong signal. But there is one assumption we have taken in this whole process, is that there should be no coupling between the spin. So here we have completely ignored the spin-spin coupling phenomenon. So now we will include the coupling also. So imagine an AX coupled system where so it's a A is interacting with X and X is interacting with A. So both A and X split up into doublets. We have seen this in the previous class. And the frequency difference between the doublets is called as the spin-spin coupling constant. Now, imagine we are, so you have this AX system. So A splits into two lines, A1 and A2, and X also splits into two lines, X1 and X2. Just to refresh what we did in the previous class, basically the energy levels that give rise to this kind of splitting is that, so A has alpha and beta spin and B also has alpha and beta spin. So alpha alpha is where both A and X are alpha and it is the lowest energy level. Then you have two degenerate energy levels, alpha beta and beta alpha, and your highest energy level is beta beta. Now, there can be two kinds of A transition. The one shown here, in which X remains as alpha, but the A is going from alpha to beta, and that has been termed as A2. And this transition, where again X remains beta, but A is going from alpha to beta, and that has been termed as A1. So now let us consider the A system. So A system has two spins, A1 and A2, shown by two blue arrows here. So when the A system undergoes a 90x pulse, both A1 and A2 from Z axis, they will come down to the Y axis. So this here just the transverse plane has been shown, but you can correlate with this. So it was in Z and then it came along Y after the 90x pulse. So after the 90x pulse, both the A1 and A2 are along the Y axis. After that, then a time tau is given. During this time tau, A1 and A2 will precess at different speeds and they will separate out because A1 and A2 have different frequencies. So they will have different speeds of precession and they will separate out. Here it is shown that A1 is going in an anti-clockwise direction and A2 is going in a clockwise direction. Then this 180y pulse. Now it is important to remember that when you apply a 180y plus, this 180y is applying both on A and on X. So we are breaking up the 180y pulse into 180A and then 180X. So first, when you apply the 180A, what happens? So basically what 180A means is that A will go from alpha to beta. That is what 180A means. So what does this mean is that this level will become beta alpha. This level will become And this level will become sorry, just 1 second, ignore this. Yeah, so 180A means that the A goes from alpha to beta. So what that basically means is that A2 and A1 will change. So how can we say that? Yeah, so this 180x pulse we saw in the previous, you can break it up into x and y components. So you can break both of these up into x and y components. You can break the lower one also into. So when you carry out a 180y pulse, what we had seen here, 180y is flipping the x component and y component is remaining unchanged. That is what is happening. If you flip the x component and you keep the y component unchanged, then A1 and A2 will exchange. But you have to remember that the direction will not change. So A1 was going in the anti-clockwise direction. A1 is still going in the anti-clockwise direction. And A2 was going in the clockwise direction. A2 will be going in the clockwise direction. Now, so out of the 180y, we have so far applied 180a. Now, if we applied 180x, if you apply 180x, basically this, yeah, now is what I was saying. 180x means the x component is going from alpha to beta. So this will become beta beta. This will become alpha alpha, and this will become beta alpha. So in the energy state, you keep the alpha A same, and the alpha x you flip from alpha to beta and beta to alpha. That is what 180x means. So what this means is now the A1 transition has become A2 transition. See, A1 was between alpha beta to beta beta. Now in the new energy states, alpha beta to beta beta is this transition. So A1 has come here, and alpha alpha to beta alpha was A2. And if you look at this red state, alpha alpha to beta alpha, so this transition has now become A2. So A1 and A2 have interchanged. So here you write it in, so A2, where A2 is there, you have written A1, and where A1 is there, A2 is written. Again, the direction remains same. A1 continues in the anti-clockwise direction. A2 continues in the clockwise direction. So now the 180y has completely acted both on A and on X. Now when you allow it a time tau, you can see there is no refocusing of A1 and A2. A1 and A2 will continue to diverge even more. So at the end of the spin echo period, this coupling has not refocused. So when you have two coupled spins, A and X, they will remain coupled after the spin echo phenomenon. They will not refocus back into a single spin. So we will come into the advantage of this later during this discussion, where you will see so that this J value that is there between A1 and A2, the J value information will be retained, because suppose A1 and A2 are merging back again, that means it is decoupling. So from this spectra, it is becoming a single line. Then your J information will be lost. But this is not happening. A1 and A2 remain different. They are pointed in different directions. So the J value information will be retained, and we will use this later. So here, again, the spin echo only is shown. One thing to remember here is that while the spin echo everything is happening, the transverse or T2 relaxation will always be there. So your T2 relaxation is an inherent phenomenon. You cannot stop that. So even though the spin echo everything is happening, so it is coming 90-degree in the y-axis, then it is precessing in the transverse plane. But during all of this, the T2 relaxation will continue. So T2 relaxation was basically the tendency of the spin to go back to the z-axis. That is always there. So because the T2 relaxation is there, it makes the spin echo an ideal method to measure T2. Like I was saying, suppose there are field inhomogeneity. Field inhomogeneity basically means from Z, by applying a 90-degree pulse, you have brought it to the Y. Now, this should be a single spin, but because the field is inhomogeneous, this is breaking up into multiple spins. Now, if there are multiple spins like this, then each of these will have a different T2. And so that will not give you an accurate measurement of T2. But if you follow the spin echo pulse sequence, what happens is that when you flip it through 180-degree, refocusing will happen. We have seen previously also that the spin will get refocused in the same direction. Here also you can see that spin is ultimately all the inhomogeneities are getting refocused back in the y direction. So if you measure T2 at the end of the spin echo, there will be no field inhomogeneity. So you can measure the T2 accurately. So after the spin echo, you just, so echo is measured here. After that, you give it time to T2 time to relax back to the Z state. Then if you just measure the T2 time, you have a detector along the y-axis. The T2 time will be the time in which the FID is completely decaying to zero. So if you measure that time in which the FID is completely becoming zero, that is the signal is decaying back from Y to Z, then you can accurately measure T2. So this takes care of all your field inhomogeneities because ultimately the spin echo causes the signal to refocus. So that is an application of spin echo. It is used to measure the T2 relaxation. This is another application of spin echo which is used for water suppression. So here the pulse sequence is like this. So you have your normal 90x pulse. That is, in any pulse sequence, you always have the 90x pulse at the beginning. Now there is here a special pulse is applied. You can see this kind of rounded pulse. What this means is that it is a soft 90 minus x pulse. So soft pulse basically means a selective pulse which you are applying only on one signal. So this kind of rectangular signal means that you are applying this 90-degree pulse to all the frequencies. But if you have this kind of rounded signal, that means you are applying this 90 minus x pulse only to that of water. Here water is chosen. Some other signal can also be chosen. So first, a 90 minus x pulse is applied selectively on water. Then a 180x pulse is applied on all the signals. You can see again, this is a hard signal. And after that, once again, a 90 minus x soft pulse is applied on the water. And after a certain time tau, the signal is collected. There is another additional thing here, that is the linear field gradients. So normally we consider a constant field H0. But in this case, the field is changing. So if you have the solvent tube here, there are coils around the solvent tube which change the field. So suppose this is the solvent tube, bottom to top, the field will change. So at any point from bottom to top, field can be written as H0 plus GZ, where H0 is the basic field that is applied and GZ is the field gradient along the z-axis. So along the z-axis, this magnetic field is changing. So you are introducing a varying magnetic field. So what will happen? After the 90x pulse, all your signals, whether it is water or your sample, will come in the xy plane. Here the xy plane is shown. Now the red one is the sample. So let us first look at the sample signal. So the red one is the sample, and the sample signals have all come along the xy plane. Now, because of the field, this kind of varying field, we have previously seen that if there is field inhomogeneity, the single signal will split up into multiple signals. Here you're introducing a field inhomogeneity by putting a varying magnetic field. So the single signal will split up into multiple signals in different directions. After this, so the 90 minus x pulse will not act on the sample because they are selective soft pulses given only to water. Here we are looking at the sample. So the sample will only see a pulse of 180x. What this 180x will do, it will completely flip the signals to the other side. You can see the same thing has happened here. The signals were around this side. After the 180x, the signals have all flipped 180 degree to come to this side of the sphere. Now, if you give it a time of tau, so the direction of the signals again will remain same. If the ones here are anti-clockwise and the ones here are clockwise, after flipping also the directions will remain same. So if you give it a time tau, they will now come together into a single signal and refocus. That is the illustration here. You can see all the signals are again refocusing back into a single line. So that is what is happening to the sample. But what is happening to water? Now in water, the first part is same. It is facing a 90x pulse. So all the magnetization is coming in the xy plane. But now, if you look at the total effect on water, water is facing a net pulse of 0 because it is facing 190 minus x, 290 minus x. So basically 180 minus x and 180 plus x, which is 0. So water is not facing any pulse. The net pulse on water is cancelling out. So what will happen if the net pulse cancels out is that these will continue moving, and ultimately they will spread out. So phase will spread out. If you remember the hypothesis of random phases, that is what is happening. All the phases will spread out equally in all directions. So that will lead to cancellation of the water signal. So the water signal is cancelling out and your sample signal is refocusing. So you will get a very strong sample signal without any signal of water because it has cancelled out. In other words, the water signal has been suppressed and the sample signal remains strong. So this is how spin echo is used for water suppression, and it is called the Watergate sequence. So here an example has been shown of water suppression by Watergate. So this is the spectra of phenylalanine. In this first spectra is basically it is the spectra without water suppression. You see, you can only see the peak of water and nothing else. The second spectra, basically you have increased the intensity of the first spectra till you are able to see the compound peaks. But what this will happen, so this broad peak is the peak of water. Now, if you keep increasing the intensity, you are scaling up the spectra till your other peaks are visible. The problem is that if there is any peak hiding below the water peak, you can't see that. It is completely masked by water. The third spectra is one where Watergate has been used to suppress the water. So you can see here the water is very much suppressed, and now any small signals you can see. So suppose there was one signal very close to water here. Now you will be able to see that, whereas in case of this, it will be masked by water. So this is an application of Watergate to suppress the water signal and observe the other signals of the sample more clearly. Now we will come to another concept, which is basically dynamic NMR. So suppose you have a proton which is flipping, which exists in equilibrium between two states A and B. So suppose the proton is sometimes on A and sometimes on B, and the rate of the forward is K1 and rate of the backward reaction is K minus 1. So now if this rate is very slow, you will be able to see two distinct signals, one for A and one for B. But as the rate of exchange is increasing, the signals will slowly merge or coalesce till only one signal is seen. Because the flipping is so rapid, the proton is so rapidly exchanging from A to B, you are not able to properly distinguish the signal of A to B. In that case, only one signal will be observed. So that is called fast exchange. So slow exchange is basic. So we define something called the exchange rate, K(EX), which is the summation of the rate of the forward and the reverse reaction. If this exchange rate is much less than the frequency so the frequency difference is this, and if the exchange rate is less than the frequency difference, then you will be able to see both signals of A and B. And in fast exchange, the exchange rate is much greater than the frequency difference. Then you will only be able to see one signal. And this one signal is basically a weighted average of A and B. So if you look at the frequency at which A and B are appearing, this in case of the merged signal, it is not exactly in the midpoint of A and B, because the population may not be same. So the actual formula, so this is called frequency observed, which is the merge frequency, is PA omega A plus PB omega B, where omega A and omega B are the frequencies of the A and B states, and PA and PB are the populations of the A and B states. So if the populations are identical, in this case, this is basically a simulated NMR. So in this simulation, you have assumed that the populations are identical. So PA and PB is equal and it is half. That is why in this case, the observed frequency is exactly in between these two frequencies. But we'll see some practical experimental NMRs later, where the observed frequency is a weighted average of the two frequencies. Now, coalescence is that point where they have merged. So in this exchange rate, you can still see two separate peaks. But the point at which both have merged, that is called coalescence. And this is a condition at coalescence that tau, okay, so we'll define another thing called tau, which is the lifetime of the individual state. So lifetime is basically reciprocal of the exchange rate. So you can see this equation here. K1 is 1 by tau A. So tau A is the lifetime in state A. And similarly, K minus 1 is 1 by tau B. So the lifetime tau A and tau B is the reciprocal of the rate constant. So this is a condition. We don't need to know the derivation of this formula, but this is a formula that exists, that at coalescence, when the two signals have merged, tau into omega A minus omega B is 1.414. So this tau is basically the net tau. So tau A is related to the rate of forward reaction, tau B is related to the rate of the inverse reaction. K exchange is a term we have defined, which is a summation of the forward and reverse rates. Now 1 by tau is basically the net lifetime. So when it is merging, it is like a single state. The reciprocal of the K exchange is defined by 1 by tau. So this tau is basically the summation of the reciprocal of the lifetimes of the two states. If you take this tau and multiply it by omega A minus omega B, you will get 1.414. So how does this equation help you? Basically, if you take the spectra where slow exchange is happening, you can find omega A and omega B. Then using this formula, you can find out tau. And if you know tau, you can calculate the K exchange. So this is basically called dynamic NMR. That is, the NMR spectra is not constant because the proton is hopping between state A and B, and that is why it's called a dynamic NMR. In this case, a two-site exchange. Now, this is the same the dynamic NMR in experimental conditions. So here you have a compound where you have a partial double bond. So you know that this N can donate a lone pair here, and so this bond will have partial double bond character. So these two CH3s are not equivalent. One you can consider as cis to this N double bond N, and one is trans to that N double bond N. So the chemical environment is clearly different. So these two will appear as two different signals in case of slow exchange. Now, as the temperature increases, the rate of, I'll just remove this. Now, as the temperature increases, the rotation around this bond shown by the arrow increases. So when that happens, the two proton signals will start exchanging. And so slowly they are merging. And you can see this is the point of coalescence where you can no longer distinguish the two signals. Now here one thing you can note is that this omega, we called it the omega observed. So the omega observed here is not exactly in between these two signals, A and B. It is not exactly in the middle. And this is what we were discussing, that omega is a weighted average. It depends on the population also. So if the populations are equal, then it will be exactly in the middle of A and B. But in this case, populations are not necessarily equal. So the omega observed is slightly shifted. Similarly, you can have this kind of system where you have two sets of coalescing proton. So this is one set. So these two are exchanging among themselves, and these two are exchanging among themselves. So you can see here that at lower temperatures, minus 138 degrees Celsius, very clearly the signals are seen. But then you have a coalescence temperature where the signals are merging. As you are increasing temperature, the signals are merging and you have coalescence. So one consequence of exchanging proton is we have seen that with the increase in temperature, the signals are merging of the exchanging protons. Another consequence is that the coupling constants will average out. So suppose you have A and B protons, they are splitting each other. So no, actually, they are not splitting each other. They are different systems. So suppose you have A proton that is split into a doublet and B proton that is split into another doublet. And the splitting constant in A, you are calling it J1, and in B, just 1 second, I think. Right, so I'll continue. So another consequence of the exchanging protons is that the coupling constants will get averaged out. So suppose you have the signal of A and you have the signal of B, and A is split into two signals, A1 and A2, with a coupling constant J1, And B is also split into two signals, B1 and B2, with a coupling constant J2. Now, what happens? So when A and B are merging, so suppose this is the merged peak of A and this is the merged peak of B. So at that time, J1 has also disappeared because both of these are merging, and J2 has also disappeared because these are merging. So you will observe an average J which depends on the population of A and B. But this average J does not give you any information because you know that, so this is a 1-3 coupling constants. There are 3 bonds between this hydrogen and this hydrogen that are coupling. This J value is dependent on this torsional angle. So if you know the individual J value, you will know the individual torsional angle. But this kind of average J value is meaningless. It does not help you in any way. So that there is a way to counteract this. We will come to that. But before that, there is another concept that we'll go through, that is the polarization transfer, also known as nuclear Overhauser effect. So basically what is done in this effect, suppose you have a spectra consisting of many peaks. Each of these peaks may be due to different protons shown here as A, B, C, D. Now you are selectively perturbing one proton, that is HA. Here you can see only HA is being perturbed. What does it mean when you say that you're perturbing HA? It means, so suppose HA, this is HA. HA has two states, alpha and beta. When you are perturbing HA, that means you are supplying a radio frequency to HA and you are changing the population of alpha and beta. You can change the population such that the populations become exactly equal. You know, when the population of alpha and beta are equal, the signal of HA will vanish because any signal that appears is due to this population difference. So if you can perturb the HA and cause that particular signal to vanish. But eventually the populations will try to come back to their original population, which is called the spin lattice relaxation. So when the population of HA goes back to the equilibrium population, this energy will again be released. And this energy or perturbation will now affect another spin. So it will reflect in the signal intensity of that spin. So that is what these black arrows show. You are perturbing HA, that is, you are changing the population of HA. But the perturbation will not be restricted to HA because eventually HA will come back to the equilibrium population and the energy will then be transferred to the neighboring, by neighboring I mean those protons that are close in distance. So the energy or perturbation is getting transferred to HB and HC, and this kind of coupling is called dipolar coupling. So here the perturbation is being transferred or relayed, and that is why this is often called polarization transfer, because it is transferring the perturbation from one spin to another spin. So how will the spectra look like? So spectra 1 is one where basically you have not done any perturbation, or you can imagine that the perturbation does not match with any frequency. Just 1 second. I think someone is, can just. Yeah, so this is the control case where you have applied a radio frequency that is completely off resonance. So this radio frequency is not absorbed by any proton. It just, it is not affecting the spectra in any way. So this is the control spectra. The second spectra is where you have specifically perturbed. So you have seen, so suppose you have specifically perturbed HA. So the signal of HA will completely vanish. So you can imagine this is here. There is no signal here. So the signal of HA has completely vanished. And the signal of the other protons which are close to HA will also be changed. So this is called the perturbed spectra, where only the protons which are close to HA in distance. So imagine HB and HC here. They are close to HA in distance. So they will also get perturbed and their signals will change. But other protons have exactly the same signal in 1 and 2. Now the different spectra is taken. So the two spectra are subtracted. So HA, from positive, it is becoming 0. So if you do spectra 2 minus spectra 1, HA will come in the negative direction. And HB and HC, here we are imagining that suppose HB was here, here the intensity has increased. And again, suppose HC was here, here the intensity has increased. So if you do 2 minus 1, you will get a positive intensity for B and C. And these are called relayed perturbation because the original perturbation has been transferred to these protons. So what this spectra will tell you is that which are the protons that are close to the perturbed proton. And so it will give you an idea of the structure of the macromolecule because it will tell you which protons are close to proton A and so on. There is a formula here which gives an idea about the extent of the nuclear Overhauser effect. And the formula is given by this. NIS. So basically, S is the spin you are perturbing directly, and I is the spin to where the perturbation is being transferred. In the previous case, HA, which you were directly perturbing, is your S, and this B and C, where the perturbation is getting transferred, is your I. This can be written as, in the numerator, it is II minus I0 divided by I0, where II is the perturbed intensity of spin I, which is this increased intensity. And I0 is the equilibrium intensity of spin I, that is the intensity in the control. So you're just subtracting the intensity and dividing by the control intensity to get an idea of the extent of this nuclear Overhauser effect. This NOE is dependent on various factors, which we'll see in the coming slides. So one thing is that NOE depends on molecular motion. Here we will define a constant tau c or correlation time, which will tell us how fast the molecule is moving inside the solution. If you have a small molecule, small molecules will move very fast. So the tau c will be very small, 10 to the power minus 10 to 10 to the power minus 12 second. This is also called extreme narrowing limit because it's a very small time limit. So in small molecules, the time for tumbling of the molecule is small. And in this case, the NOE extent is given by half gamma A by gamma X. So in the previous slide, we were defining this as I and S. So here we can write this as NIS. So S or A is the one you are directly perturbing, and I or X is the one where the perturbation has been transferred. It in terms of gydomagnetic constant, it can be written as half gamma A by gamma X for small molecules. And for large molecules, so large molecules will take time to tumble inside a solution. If you imagine a large molecule like a protein or DNA, the correlation time will be bigger. It is 10 to the power minus 8 to 10 to the power minus 9 seconds. And in this case, this extent of NOE is given as minus gamma A by gamma X. So you don't need to worry about the derivation of these formulas. You can just remember the formulas by themselves. So one example is shown here. Suppose you have a small molecule like suppose methane, and you have here A is the 1H and X is the 13C. So basically you are perturbing the 1H and you are observing the transfer of perturbation to the 13C. So this NXA, we are assuming a small molecule, will be half into the gydomagnetic ratio, the gydomagnetic magnetogyric moment that is there, or gamma, the ratio of A by X. We know the ratio of the gydomagnetic of hydrogen by carbon is around 4. And so half into that will give you 2. So what this means is that the signal of carbon will increase 2 times after NOE. So if you imagine this, so suppose this is the signal of hydrogen and you have signal of carbon. After you are perturbing the signal of hydrogen, the signal of carbon will increase 2 times in intensity according to this formula. So this is an advantage of the NOE. We know so if we can increase the intensity of the 13C signal, that is always a good thing, because otherwise normally when we take a 13C spectra, we have to take very high concentrations because the population of 13C is so low. But NOE is a method where we can just increase the intensity of the 13C signal. Now, suppose, so that is one advantage. Now, that is obviously only for small molecules, because in large molecules, that large molecules, it will be even greater actually, because if you do minus gamma A by gamma X, in case of large molecules, it will be -4. So the NOE will increase, but it will increase in the opposite direction. So the control spectra will be something like this. And after NOE, this will increase 4 times in the negative direction, and this will become 0 because it is the one you are perturbing. Now this graph, basically, let us assume homonuclear, so both as hydrogen. So if we do that, gamma A and gamma X will cancel out. So this value of NXA, that is what is there in the y-axis, it will have a positive value of half and a negative value of -1. So the NXA will go from half to -1 as a function of tau. So as you can see, as tau is going from small to large, as tau is going from small to large, the NXA is also going from 0.5 to -1. In small, it was 0.5, in large, it was -1. So this is a graph that you can just remember. So this was a steady state NOE because you are not changing anything. Now we will talk about a transient NOE where we are giving something called a mixing time. So in this case, what happens is that we are, so suppose this is your original spectra. We are selectively inverting. So previously you saw in the Watergate that this kind of rounded pulse means that we are selectively giving that pulse to one signal. Suppose we give this 180x pulse selectively to this signal. So this signal will get inverted. So it has come in the negative direction. Others are same, or they are affected according to the to how the perturbation is getting transferred. So if you take the different spectra, so this is 2, this is 1, different spectra is 2 minus 1. So the one that you are selectively inverting, this signal will come as negative. And the other spectra, so because of, so you're perturbing this signal and the perturbation is getting transferred to other signals. and the intensity of the other signals where the perturbation, so perturbation is getting transferred to this signal and to this signal. Their intensity can increase or decrease. So the different spectra will basically show those peaks where the perturbation is getting transferred. Now, if you understand this with respect to the pulse, in the pulse, you are giving a selective 180x to suppose you have two spins, you are giving a selective 180x to the black spin. So the black spin moves to the to the minus z axis, and the red spin remains along the z axis because you're not doing anything. And now as the black spin is recovering, so slowly this black spin will come back to the z axis, and when it is coming back, it will release an energy. This energy is taken up by the other protons. So we have here shown that these two protons are getting perturbed because of the perturbation here. So because of the perturbation on this black arrow, the spins of these protons are getting affected. This tau m is a time you have given for this transfer. So as the perturbed spin is recovering, the perturbation is transferred to other spins, and this will cause a change in intensity of these other spins. As you can see, so you have perturbed this spin from z to minus z. Now it will tend to go back to its equilibrium position, that is z, and while it is going back, it will release energy. This energy is picked up by the other spins which are close to it, and the signal intensity of these spins can increase or decrease. In this case, it has decreased, and so they will show up in the different spectra. For other protons which are not affected by this perturbation, the spectra will be exactly same in the control and the perturbed spectra, so it will cancel out in the different spectra. Now you might think that suppose we are perturbing this hydrogen and the perturbation is getting transferred to the hydrogen close to it. So now this hydrogen is perturbed. But once this is perturbed, it can perturb the hydrogens close to it. So it is kind of like a relay process. If you're perturbing one, the perturbation is transferring to the hydrogen close to it. From there, it will transfer to the other hydrogens close to it, and so on. After around 4 to 5 transfers, it generally dies down. So this kind of thing is called spin diffusion, because the perturbation is diffusing through the system. And the spin diffusion is directly proportional to tau m, because longer the tau m you give, longer time it has to diffuse through the system. So what happens in case of this? So if you give a longer time, the NOE changes like this. Normally, we consider this an approximation. We consider a linear approximation. This NOE again is basically what we were talking about, NIS, before. So as the tau mixing is increasing, the NOE is also increasing. And after a certain time, it will plateau down and go. But we consider up to the linear portion. So we generally consider up to this portion, and if we take this approximation, we will get that what we have written as sigma ij, you can again write as NIS. These are just different ways to write the same thing. It is directly proportional to 1 by Rij to the power 6. So the distance between the two hydrogens that are interacting to the power 6. So suppose perturbation is transferring from this hydrogen to this hydrogen. Then distance between these two hydrogens is Rij, and 1 by Rij to the power 6 defines the extent of NOE. So basically from the NOE, you can calculate the distance between different protons. And using this distance, you will have an idea of the structure of macromolecules. Suppose you have a helix, protein, you have a helix, and you have one hydrogen here and one hydrogen here. So in these two hydrogens, you will have a NOE transfer because they are close to each other. Using the extent of NOE transfer, you can find the Rij or distance. And if you know the distance, you can predict that whether it will be a helical structure or it will be some other structure. That is how the knowledge of the distance can give you a knowledge of the three-dimensional structure. So NOE has two objectives basically. One is that the signal of less sensitive nuclei is enhanced. We have seen before in case of, we saw that when it is 1H and 13C, the signal of the 13C is increasing 2 times. So 13C is a less sensitive nuclei, you are increasing the signal of that. And the other objective is that you can find out the structure of macromolecules, which I just discussed. Now we'll come to another phenomenon called selective population inversion. Just give me 2 minutes. Right. So consider a two-spin system, AX. We know that the energy levels of the AX system is basically alpha alpha, alpha beta, beta alpha, and beta beta. Now, if we consider the population. So we have considered the population of the lowest level to be delta plus delta. Population of these two levels. So basically, wherever alpha is becoming beta, the population will invert. So here it was delta plus delta. In beta alpha, it will become minus delta. The population has inverted plus delta because second one remains as alpha. In alpha beta, it will be delta minus delta. And in the upper one, it will be completely negative of the lower, that is minus delta minus delta. Just remember that when going from alpha to beta, the population inverts. So again, you have four possible transitions. So for the A nuclei, you will have two transitions here shown by A1 and A2, where the first nucleus is going from alpha to beta, and again, it's going from alpha to beta. So, in case of the X nucleus, you have X1 and X2, two transitions. Now we know that the intensity of the signal will depend on the population difference. So in case of A1 transition, if you can see the population difference is 2 delta. And in case of A2 transition, population difference is again 2 delta. And in case of X1 and X2, the population difference is 2 small delta. So this is how the spectra is expected to appear. Here we have taken one assumption. We have assumed capital delta is greater than small delta. And that is why the signal with 2 capital delta intensity we have shown as greater. That is one assumption we have taken. Now we will selectively invert the A1 population. What does this mean? Again, you imagine 4 energy levels. Population of beta beta remains same. Population of alpha beta also remains same. But these two populations will invert. So this population and this population will exchange. So the alpha alpha will have a population of minus capital delta plus small delta, and beta alpha will have a population of delta plus delta. Now what will happen if you again imagine this intensity? So this is your A1 transition. Now the population difference is -2 delta. So your intensity remains same, but it comes in the negative direction. And in A2, it remains same. So it was 2 delta here, it remains 2 delta. And one major thing that happens is that X1 and X2, if you again see the population difference here, earlier the intensity was small, 2 small delta. But now the population difference, due to this inversion that we carried out, the population difference in X1 and X2 has greatly increased. So the signal intensity has also increased. X1 will become -2 capital delta plus 2 small delta, if you just see this population difference. And X2 will become 2 capital delta plus 2 small delta. So the advantage of this selective population inversion is that you can enhance a so in the equilibrium population, this signal was low intensity, and now you have managed to increase the intensity of this signal. That is the advantage. But there are also certain disadvantages. One thing is that you have both positive and negative signals. And you know, in NMR, we generally we want the spectra in such a way that all the signals are positive. So that is a disadvantage. Second thing, you cannot decouple A and X. So suppose, what is decoupling? If you decouple this, you will get a single peak. If you decouple this, you will get a single peak. But if you decouple this or this, they will cancel out because they are in opposite phase. So you cannot decouple them. Secondly, this kind of selective inversion requires long pulses. And finally, this selectivity may be difficult in complex spectra. So here there are only 4 energy levels. You can selectively inverse the population of 2. But suppose there are 10 or 20 energy levels, then it is very difficult to carry out this kind of selective population inversion. So another method that was like, there are so many disadvantages of the SPI. So another method to improve this was introduced that was called INEPT. That is insensitive nuclei enhancement by polarization transfer. So we'll slowly go through what happens in INEPT. The first part of INEPT is very similar to the spin echo that we studied. So first, there is a 90-degree pulse that is forcing all the magnetizations. So here what we will, again, we are imagining a system, this kind of system where we have A1, A2 and X1, X2. So we are imagining the two spins A1 and A2. After a 90x pulse, from Z axis, the two spins will come to Y axis. Then you are giving a time tau, which is 1 by 4j. So you have A1 and A2, and this is j. So you take 1 by the coupling constant and you give that time tau here. What that will do is that is allowing the A1 and A2 to precess in the transverse plane. And because A1 and A2 have different frequencies, they are precessing in different directions. So during the time tau, there will be an angle between A1 and A2, that is theta, and this angle will be 2 pi tau into j. So basically, j is the difference between frequencies. So we know that angle traveled by, suppose angle traveled by A1 is 2 pi omega 1 tau, and angle traveled by A2 is 2 pi omega 2 tau. So if you take the difference in these angles, you will get the angle between A1 and A2, and that will come to 2 pi omega 1 minus omega 2 into tau, that is 2 pi j tau, because j is the difference between the frequencies. Now this angle we will set in such a way that it is 90 degree. So we will take tau in such a way that this angle comes out to be 90 degrees. After that, a 180x pulse is applied. Now, if you remember spin echo, the 180x pulse is applied to both A and X. So when you are applying 180A, the spins are flipping as shown here, but the direction of spins will remain the same. So A1 continues to be anti-clockwise and A2 continues to be clockwise. Then you have 180x. So when you have 180x, basically in 180x, we have 180x. What will happen is that A1 becomes A2. So this A1 is essentially A2 and this A2 becomes A1. Again, if you remember, A2 was moving in the clockwise direction, and because this has now become A2, it will continue in the clockwise direction. And A1 was moving in the anti-clockwise direction, and because this has now become A1, it will continue in the anti-clockwise direction. We have maintained this in such a way that the angle between A1 and A2 is 90 degrees. And you can see the angle between A1 and A2 is maintained at 90 degrees. So up to here, it was the same as spin echo. And if spin echo was allowed to continue, if you remembered, in spin echo, the coupled spin continued to separate out and gave rise to this kind of a condition, where you have one spin going somewhere here, one spin going somewhere here. So the spins were not refocusing. So that was what had happened in spin echo. But here you're adding an extra portion to the pulse sequence. Here what you're doing is that you're adding another tau equal to 1 by 4j. So if you remember, we set tau in such a way that in the time tau, the angle between the spins became 90 degrees. So the angle is already 90 degrees. If you're allowing another time tau, the angle will become further 90 degrees. So 90 plus 90, now the angle between A1 and A2 will be 180 degrees or pi. After that, you add a 90 Y pulse to A. So to the A spins, you are applying a 90 Y pulse. So the A spins are now in the X axis. When you apply a 90 Y pulse, they will go back to the Z axis. But because they were in opposite directions with an angle of pi between them, the angle of pi will be retained. So what happens here is that A1, initially you had a situation where A1 and A2 were both positive. Now A1 remains positive, but A2 is getting inverted. So if that is happening, then we have already seen that in case of population inversion, this kind of situation will happen, where we just saw in population inversion, the signal of, so here the signals of A in population inversion had become minus 2 delta and 2 delta. That is what is happening. The signal of A is minus 2 delta and 2 delta. Now, if you carry out a 90x pulse, then, so up to here it is A. And A is giving a signal like this because it is the same as the population inversion case. But if we consider the X symbol now, the X will also be, so imagine the X signal. So in case of population inversion, the X signal had come like this with minus, with these intensities which have been written here. So this figure has again been written here. You have one lower and one upper signal with minus 2 delta plus 2 delta in the lower, minus 2 delta plus 2 delta lower, and 2 delta plus 2 delta in the upper. 2 delta plus 2 delta in the upper. This is what you have at the end of the 90Y pulse on A. Because at the end of 90Y pulse, there is a population inversion. Now the pulse that we have to think about is the 90X pulse on the X. So what this will cause, initially X was having, before the population inversion, X had a small signal of 2 small delta, which was equal in intensity for both X1 and X2. Now, what the 90X pulse will do, it will simply invert the signal. That is, it will be minus 2 delta, minus 2 delta. So to get the net signal of A, of X, you have to add this and you have to add this. If you add this, the two deltas will cancel out and you will get the signal of X as, you will get one below and one above, and they will have 2 delta, that is minus 2 delta and plus 2 delta. So this is kind of a combination of spin echo and your population inversion. So what is the advantage here is that your A signal remains same. So whatever you got in population inversion in A, this is remaining same. But the advantage is that in X, these two intensities were different. If you look at the intensity here and here, the X symbols signal had different intensity. But after the inept process, the X signal also has the same intensity, both the X signals. So that is an advantage. Now, the advantage of inept, as we said, is that you can gain identical intensity for the X doublet. And another advantage is you can use non-selective pulses. So in the spin inversion, selective inversion, you had to use very specific pulse so that the population of these two levels are inverted. But when you have an inept process, these are very general pulses, 90x, 180x. There is no specific pulse. So that is another advantage. Now, if we look at so far we have done the inept for the AX. You can see, so the AX, the X signal will appear like this, one lowered and one upward, which we just saw. In X signal, one has a negative and one has a positive. Now, what if you have a A2X system? So the negative line will split into two. So earlier you had A and X. So X was interacting with only one A, and when it was interacting with only one A, it split into one negative and one positive signal. Now, if X is interacting with another A, the negative signal will split into two, positive signal will also split into two. It will give this kind of a signal, and the middle part will cancel out. So this is basically this, where you have one negative and one positive signal, and the middle signal is cancelling out because it's equal positive and negative. Then if you have another A, then again the lower will split into two and upward will split into two. That is the thing of A3X, which is here. So the disadvantage of inept is that the positive and negative signals are still present. You have not been able to remove that. And another disadvantage is in A2X kind of systems, the central signal cancels out. So how do you distinguish between A2X and AX? Because both are, A2X is also giving like this, AX is also giving like this. So that is the disadvantage that is still persisting. So now another improvement over the inept experiment is basically, so in the inept experiment, what did we see? That after, so inept experiment is basically up to here. Up to here is your inept experiment. Now this extra portion has been added. What this extra portion is doing, so imagine at the end of the inept experiment, the X transition, so X1 and X2, after the inept experiment was appearing like this, one in the negative and one in the positive, and the intensity has increased. Here it was only 2 small delta for both. Here it is 2 capital delta. So you have increased the intensity. Now you are giving a time tau. So tau dash plus tau dash, basically 2 tau you are giving. You are allowing the signals to refocus back along. So here you're putting a 180x. So ignore this 90y right now. You are basically allowing the signal to if you remember, A1 was moving in this direction, A2 was moving in this direction. Similarly, X1 and X2, they are also moving towards each other. So if you allow this time 2 tau to pass, we saw in time tau it is traveling pi by 2. So in 2 tau it will travel another pi. So they will come together. They will travel another pi angle in 2 tau time, and the signal will refocus. So now you can do decoupling. Earlier we saw that when we have signals in opposite phase, decoupling is not possible because it will just cancel out and become neutral. But now by the refocusing, we are now able to decouple the signal, because when it is refocused, it will, so both are now in the same direction. Both signals will appear together at the same frequency. So decoupling has happened. So you can do decoupling by using the refocused inept experiment. That is basically you are allowing, we saw in time tau it is rotating pi by 2. So in time 2 tau it will rotate pi, and there is pi angle between the two spins. So once it rotates through the pi angle, both the spins are now in the same direction. That is, both the spins can now be decoupled. So that is another variation of the inept experiment. Now we will see the basics of 2D NMR. So basically a protein or a DNA has very large number of protons, like 400 to 500 protons. So if you just see the 1H NMR, it is very much crowded. There is no way to possibly assign any signal to this 1H NMR. So for this, it was thought that 1H NMR includes only one frequency or one time axis. So somehow if another time axis can be introduced, the crowded nature of the spectrum can also be resolved. So then two-dimensional NMR was introduced. Basically in two-dimensional NMR, there is a preparation time. Preparation is basically the initial pulse you apply, which is generally 90x. Then you are allowing a evolution time or T1, and this is the time in which the spin is moving along the transverse plane. So after your preparation time, the spin has come from the z-axis to the y-axis. And then the evolution time or T1 is when the spin is moving around in the xy plane. Then mixing is allowed. Mixing basically means you allow the perturbation in the spin to transfer to other spins. So you can see mixing establishes correlation between frequencies. So if you have two spins which are near each other, the mixing time is basically allowing the perturbation in one spin to transfer to another spin. And after the mixing time, you are giving a time T2 in which the FID is collected. So this is basically the time in which the FID is collected. So now you have two times T1 and T2. What happens in the 2D experiment is that the T1 time is not constant. It is varied. Initially, it starts from 0, and then it is increased in equal intervals. We consider each interval as delta T1. So it is delta T1, 2 delta T1, and so on. The T1 time is increased. And T2 time, so according to the difference in T. So suppose when T1 is 0, you get a certain FID. When T1 is delta T1, you get a different FID. Like that, a series of FID is generated. So you can see here, there is a series of FID. And now there are two time domains. One is the time domain within the FID itself. So if this is the FID, there is one time domain that is here. And another is the time between each FID. So if you compare FIDs 1 and 2, they are varying in this T1. So that is the second time domain. If you carry out a two-dimensional Fourier transform, it will give rise to this kind of spectra, where in the x-axis also you have frequency, y-axis you have frequency. So we have called these T1 and T2. We will call the frequencies nu1 and nu2. So depending on the two time axes, you have two frequency axes. And this is what the basics of 2D NMR is. So if we look at it in a more detailed way. So imagine since T2 is where we are detecting the FID. So as I said, depending on T1, we will get different FIDs. So suppose we are getting one FID like this. If you are carrying out Fourier transformation, we are getting a certain frequency. This is another FID, we are getting a lower frequency. Another FID might give us a completely zero frequency or a negative frequency. So we are getting many different FIDs based on how the T1 is changing. And like that, we are getting many different spectra in the frequency axis. This is the T2 and F2. Now in the F2, we can consider many different points, A, B, C, D. These are all points along the, so A is this point, B is this point. So there are different points along the spectra that we have considered. And now we will see the evolution of these points according to T1. So point A, if you see all the FIDs, point A is always 0. So point A is always 0. If you see point B has a slight negative dip. If you carry out the Fourier transformation, it comes like this. Similarly, it is done for all the different points. So this is how the second frequency axis is generated. So you have two time axes, one along the FID and another time axis is how the different points in this frequency is changing according to T1. So basically two Fourier transforms are carried out to get two frequency axes. And this is independent. That is, we can carry out T1 to F1 first and then T2 to F2 or the other order. The order does not matter. So this is a special kind of 2D NMR, which is called a 2D J-resolved spectroscopy. So the initial part of this is similar to the spin echo. In spin echo, you have a 90x pulse followed by a time period tau, then 180 pulse followed by another time period tau. That part is similar. So this part that you can see in the arrow, that is similar to spin echo. Now in spin echo, we have seen that the J value is, the chemical shifts are getting refocused. So if you go back to slide 5, if you go back to slide 5, you can see that the J value information in spin echo, the coupled A1 and A2 are not refocusing. So A1 and A2 are appearing at different frequencies. And so the J value information is still retained. But the delta itself is refocusing. So here you have considered, suppose without splitting, if we don't have any spin-spin coupling, we can see that the signal of delta is refocusing, but the J values are not refocusing. So what this means is that this portion, which is shown by this arrow here, you have the J value, but you do not have delta. You don't have delta because during spin echo, the delta are refocusing. So this is before spin echo, and then after spin echo, it is coming back to the same position. So the chemical shift information is lost because all the spins are getting refocused back in the same position. But the J value information is retained because if you remember when we considered A1 and A2, they are going in different directions. So A1 and A2 are not recoupling. So the J value information is still there. Now in the time period after that, where so in the T2 period, the data collection is like a normal 1D NMR. So in a normal, after the spin echo is over, it will return. You can imagine it like a normal 1D NMR. So after refocusing, it will different spins. So this is after the spin echo. After the spin echo, different chemical shifts will again split up. After refocusing is over, different chemical spins will split up. So the delta information is coming back and J information is always there. So in the time period T2, you have the J plus delta, you have both information. So what this basically means is that suppose you have you have the two frequency axis. In one axis, you will know. So if you imagine T1 and T2 in time, so T1 is corresponding to frequency F1 and T2 is corresponding to frequency F2. So what happens is that in one axis, so if you imagine the F1 axis, if you calculate this doublet, basically will appear as two dots in the 2D spectra. And the J value, that is the difference between the doublet, will be difference between the two spots. And the triplet, this is the J value of the triplet. And again, you can calculate the difference between this. So the vertical difference. The horizontal difference is average. So the horizontal difference does not does not affect it in any way. So the machine adjusts it in such a way that this horizontal difference does not exist anymore. So this is the final spectra that you have. If you take the difference between these 2 points, you will get one J value. So I'll call it J1. If you take the difference between these 2 points, you'll get another J value, J2. And if you take the projection on this axis, you will get delta 1 and delta 2. So basically, you will get this midpoint, delta 1, and this midpoint, delta 2. So in this way, in 2D NMR, you have two frequency axes, and one frequency axis is giving you the J value, which is this axis written as J. Another axis is giving you the delta value, which is the F2 axis. So in this way, that is why it's called 2D J dissolved spectroscopy, because, or it is called JD separation, because J and delta have been separated in different axes. So this is an example of a 2D J dissolved spectra. So if you can imagine that you can draw projections. So if you draw here, so whatever ppm this is, that is your delta value. And if you take this difference, that is your J value. So this is actually a doublet. Again, if you take this difference, this is a J value This is a J value. This is a triplet. So like that, the 2D J resolved spectra will give you information about both the chemical shift and the J values. And here is something called refocused inept. We'll see this in very short. We don't need to go into the details of this at all. What you can just remember that in case of refocused inept, what happens is that you are able to distinguish between different carbon types. So refocused inept is a kind of 2D J resolved spectra, which enables you to distinguish between CH, CH2 and CH3. So like the 2D J resolved spectra, here you have J along this axis. So if you just take the difference here, you will get the J value. And if you take the projection along this axis, you will get the delta value. So that is same. But what this helps you is you can see that wherever CH group is there, you are getting two spots like this. Wherever CH2 is there, you are getting two, but with a much higher J value. This J value is much higher. And wherever CH3 is there, you are getting four spots and smaller J value. So these are very characteristic of to distinguish between the different kinds of carbon. So that basically covers whatever was taught in week 3. I'll quickly go through the questions of assignment 2. So these are questions on the assignment which was given at the end of week 2. So first question was hydrogen bond causes what? So the correct answer here is C. So whenever you have a hydrogen bond, so hydrogen bond is basically you have suppose O attached to hydrogen, and this hydrogen has a delta positive charge and it is having a hydrogen bond with another O which has a delta negative charge. So whenever you have a hydrogen bond, delta positive on the hydrogen will increase. If positive charge on the hydrogen increases, the hydrogen will be more downfield shifted. So you have the TMS peak here. Positive charge on the hydrogen increases means the hydrogen will be more downfield shifted, which is your option C. And you can see the correct answer is option C. Some more examples are shown here. So this is an example of a carboxylic acid. Carboxylic acids have very strong dimers. So this is one carboxylic acid molecule and this is another. Two carboxylic acid molecules will form very strong dimers by hydrogen bonding. This dotted bond is the hydrogen bond. And this hydrogen will have very high positive charge because it is forming very strong hydrogen bond. Because of this very high positive charge, it is so much downfielded by up to 10 to 12 ppm, which is a huge downfield shift. Another example, so whenever there is uh, hydrogen bonding which forms a ring compound, the hydrogen bonding is even stronger because of the stability of the ring compound. So this is forming a closed ring, and so the hydrogen bond is very strong, and that leads to even higher deshielding. Then you have this kind of a system where you have an intramolecular hydrogen bond. So this hydrogen is attached to this oxygen by a covalent bond, and this is the hydrogen bond. So it is forming a 6-membered ring. So this hydrogen bond is again very strong, and the delta plus on the hydrogen increases. And so it is very much downfield shifted. Normally, alcohol hydrogen appears around up to 5 ppm, but this alcohol hydrogen is appearing at 14 ppm because it is so much downfield shift. Then another question is that which proton will be most downfield shifted in this molecule? So this is butyraldehyde. So butyraldehyde, so CH3, CH2, CH2, CHO. So we know about the anisotropic effect. Whenever you have a C double bond C or a C double bond O, and you apply an external magnetic field, then the electrons in the pi bond will rotate, and this will give rise to an induced magnetic field shown as Bi. The direction of this induced magnetic field on the inside of this double bond will be opposite. So on the inside of this double bond, the direction of the induced magnetic field shown by red is in the downward direction, and the original magnetic field is upward. But near the area of the hydrogen, you can see the induced magnetic field comes back in a circle, and near the area of the hydrogen, both B0 and Bi are upwards. So the hydrogen will experience a net field of B0 plus Bi. So the hydrogen is experiencing a greater net field. And we know that as the net magnetic field increases, the energy difference between the alpha and beta state increases, which means the frequency increases. And if the frequency increases, the delta also increases. So the hydrogen that is directly attached to C double bond O, that is this hydrogen, the delta will be very high. Chemical shift will be very high. Because not only is it facing the electron withdrawing effect of of O has an electron withdrawing minus I effect, but it is also additionally facing this kind of anisotropic effect. So the most downfield shifted proton, that is the greatest delta, will be of the proton of the carbonyl group. That is option A, because of this anisotropic effect. If this was a benzene ring, we would have called it ring current effect. Because it is C double bond O, we are calling it anisotropic effect. Then the question was that in a quadrature detection, carrier is placed where and requires how many detectors? So this concept also we have seen in the previous class. Basically, quadrature detection is when the carrier is in between. So this is your spectral width, and you have signals in the negative direction as well as the positive direction of the carrier. So the carrier is in the middle of your spectra, and two detectors are needed because you need a detector to measure the signals in the negative direction and a detector to measure the signals in the positive direction. So the correct answer is B, where that is the carrier is in the middle of the spectra here, and two detectors are needed to measure the signals on both sides. Then you have a question asking that folding of signals in NMR occurs when? So basically, again, I'll briefly go into what folding was. When you have a spectra, so the spectral width is shown by this arrow, and if you have a peak that is lying outside the spectral width, so this can happen in case of single channel detector or in quadrature detector, that your peak is lying outside your spectral width. At that time, what happens is that the signal is lying outside the spectral width. So folding of the signal happens. That is, the signal, if you imagine that from this line, if you imagine it kind of gets folded back here, or it gets folded back here. And the phase changes into negative phase because this is kind of an instrument error that happens. So this is called folding of the signal. And when it happens is that when we take the spectral width smaller than required. So if we take the spectral width smaller than required, somehow the instrument will try to fit the signals that are lying outside within this part, and it kind of folds the signal into the part. So the folding occurs when smaller spectral width is there, that is option A. Then you have this question. The question says that a molecule with two protons coupled to each other produces a spectrum of 4 lines. Now I have imagined the 4 lines here. The chemical shift of the two protons are 2.7 ppm and 3 ppm, and the coupling constant is 10 Hertz. The intensity of 4 line in decreasing order of frequency is what? Now, if nothing is mentioned, normally we consider lines of equal intensity like this. That is what we have seen, whether in this class or in the previous class. Whenever we are splitting in a AX system, if nothing is mentioned, we generally consider lines of similar intensity. But in all the options, nowhere can you see lines of similar. So in all the options, you can see the intensity is differing. There is no option where there are lines of similar intensity. So here I will introduce a new concept that has not been discussed so far. Basically, what happens is that this is your ideal case of AX spectra, which we have studied, where your delta delta, so delta delta is basically, delta delta is this distance. Delta delta is much greater than your J. This is the ideal case we have studied. But as the delta delta becomes gradually equal to J, what happens is that the inner line intensity increases and the outer line intensity decreases. And this continues till eventually delta delta is zero. That is, both the protons appear at a same place. So this is a phenomenon that happens, that whenever the delta delta and J are coming close to each other, the inner line of the doublet will increase in intensity and the outer line of the doublet will decrease in intensity. Now that you know of this phenomenon, you can see, so if the inner line is increasing in, we have to imagine a spectra like this. I'll call this 1, 2, 3, and 4. Where inner line has increased in intensity, outer line has decreased in intensity. In that case, it only matches with option A, where you can see inner line is, so 1 and 4 should have lower intensity, 1 and 4 have lower intensity, and 2 and 3 have higher intensity, 2 and 3 have higher intensity. So it can only be option A. Next, it is asking that in NMR, the loss of small signal of sample due to large signal of solvent is called what? And we have already seen in the previous class that this is called dynamic range problem. So when you have a large solvent signal like water and small sample signals, this is why water suppression is needed, because in the digital storage range, you need to be able to store the intensity ratio of the signals. But the intensity ratio of water is so much higher than the intensity ratio of the sample that the sample signal completely disappears. So this is called dynamic range problem, which is your option B. And if it was asked that how to solve this, then this would have been solvent suppression. Then you have the question that zero order phase error in NMR spectra, what happens? So zero order phase spectra is, so what we learned is that the ideal case is when the magnetization is along Z and you apply a 90x pulse and the magnetization completely comes at Y. But in reality, what happens due to some error in this pulse, because machines are not perfect, so some error is there in the pulse. So instead of coming exactly at Y, the magnetization comes somewhere between X and Y. So magnetization will now have an X component and a Y component. So this is called a zero order phase error, because phase is basically this angle that the magnetization makes with Y. So you have a phase theta at time t0. That is at the moment where the magnetization comes down to the transverse plane. So this is called a zero order phase error, because even at time t0 you have a phase. And this does not depend on frequency, because all the magnetizations were in the z-axis and all of them together are coming in this xy plane. So independent of what the frequency of the spin is, all the spins are coming at the same place. So that is what this question is asking, that in zero order phase error, it is same throughout the spectra, meaning that all the zero order phase error is Same for all the spins. So it is option B. Then we have this question that for a molecule with large T1, the appropriate flip angle for the best signal to noise ratio per unit time by signal averaging is what? So this also we have seen, signal averaging is basically when you collect multiple FIDs, you give a certain flip angle and you give a certain time between each FID. So time between each FID and the flip angle is adjusted in such a way that on adding up all these FIDs, you get the best signal to noise ratio. We saw this graph in the previous class where we can see that in the x-axis, we have Tp by T1, where T1 is the spin lattice relaxation energy. If T1 is large, which is what is mentioned in the question, you can see if T1 is large, that means the denominator is large, so Tp by T1 is very small. It's even smaller. It will be somewhere here. So the flip angle is very small. If this is 90 and we consider half of 90 at 45, flip angle is even less than 45 degrees. In this case, that is 30 degrees, that is A. So you just have to remember this graph. You don't have to remember any of the formulas. This question is asking the NMR spectra of vinyl chloride consists of what? So this also we saw in the previous class. In vinyl chloride, you have three different kinds of protons. B, which is closest to chloride and which is most downfield shifted. Then between A and C, C is getting somewhat shielded by the electrons on chlorine. So A is more downfield shifted compared to C. Because C is getting shielded by the delta negative charge on chlorine, C is upfield and A is downfield. So you will get three signals. So if you look at the other option, two triplet means two signal. One doublet, so number of signals is 2. One doublet and a triplet, again number of signals is 2. Two doublets, again number of signal is 2. So these are all out because you need a minimum of 3 signals. Only the last option says 3 doublet of doublets. So the last answer is correct. That is option D. And finally, this is just an instrumentation question where it is asked that the purpose of liquid nitrogen is what in an NMR spectrometer. And we have seen in the previous class that you have liquid helium is there in order to bring the temperature to 4 Kelvin and cause superconducting, cause the magnet to be superconducting. But liquid helium is very expensive. So in order to minimize the evaporation of liquid helium, there is a shield of liquid nitrogen around the liquid helium, which keeps the temperature at 77 Kelvin. So liquid nitrogen is basically there to minimize the loss or evaporation of the liquid helium. That is option B. And basically that covers the questions I have. As always, feel free to ask me your doubts in your next class. And I have already posted the recording and the slides of the previous two classes. This class also I'll post in a few days.